Since the disk is uniform, we define the mass surface density, sigma, as the total mass divided by the total area, which is m over pi r squared. To find the total moment of inertia, we consider the disk to be made of many thin concentric rings. Let's pick one elemental ring at a distance r from the center with a thickness dr. The area of this small ring, dA, is its circumference multiplied by its thickness. This gives us dA equals 2 pi r multiplied by dr. The mass of this small ring, dm, is the density sigma times the area dA. Substituting our values, we get dm equals 2mr over r squared, multiplied by dr. The moment of inertia of a thin ring is simply its mass times the square of its radius. So, di equals dm multiplied by r squared. To find the total moment of inertia I, we integrate di from the center, where r is 0, to the outer edge, where r equals r. We move the constant terms, 2m over r squared, outside the integral, leaving us to integrate r cubed with respect to r. Applying the power rule for integration, the integral of r cubed is r to the power of 4 divided by 4, evaluated from 0 to r. Plugging in the limits, we get r to the 4th over 4. When we multiply this by our constants, the r terms and the coefficient simplify significantly. The final result is I equals 1/2 mr squared. This represents the rotational inertia of a uniform disk about its central axis. In summary, by integrating the mass of infinitesimal rings from the center to the radius r, we derive the standard formula for a disk. This video was generated by Vision Solve AI.